Figurines, sites, objects that museum workers label quietly. Vessel, decoration, unknown use. These are simple words for things that make archaeologists feel uncomfortable. Sometimes the ground gives up artifacts that don't belong in their layer of earth. Objects whose accuracy, whose materials, whose very purpose whispers of a science the ancient world was never supposed to have. So before the story pulls you in, take a moment to like this video and subscribe. Only if you're interested in mysteries that live in the space between evidence and impossibility. And if you're still awake, tell me in the comments where you're listening from and what time it is there. I want to imagine this question spreading across time zones, the way these artifacts spread across empires. The discovery begins not with big news, but with normal digging. In the late 1800s and early 1900s, British and French teams dug through the ruins of southern Iraq, through Uruk, Nineveh, Nimrud. Their shovels bit into clay hardened by thousands of years. They expected the usual progression: crude pottery, simple tools, the earliest scratches of writing, the standard story of civilization learning to walk. What rose from the sand instead was perfection. City walls that stretched for miles, ziggurats lined up to points in the sky, tablets documenting not basic experiments, but advanced mathematics, ratios, geometry, astronomical tables tracking Venus with an accuracy that wouldn't be matched for thousands of years. The Sumerians didn't stumble towards civilization. They arrived at it fully formed around 3200 BC, as if someone had simply switched on the lights. But among the thousands of clay tablets and temple foundations, diggers kept finding other things. Small things, unusual things. A rock crystal lens ground smooth and curved. Ceramic jars with copper cylinders and iron rods nested inside, stained with chemical residues. Diorite sculptures drilled with an accuracy that copper tools shouldn't achieve. Metal mixes containing elements not native to Mesopotamia. Most were catalogued with careful language and stored in museum basements, because these objects created a problem more unsettling than missing history. They suggested impossible history. Take the precision drilling. When you examine certain Sumerian-era stone vessels under magnification, you find drill marks that are perfectly round, cut into stone harder than the bronze tools of the age. The kind of boring that requires either techniques we don't understand or tools we haven't found. Archaeologists discovered similar strange things at site after site. Crystal lenses that actually focus light. Ceramic upper constructions that generate electricity when filled with acidic liquid. Metalwork that belongs centuries ahead of its layer. The pattern emerged slowly, not because the evidence was hidden, but because it was inconvenient. History prefers straight lines. Tool A leads to tool B. Knowledge builds up gradually, generation by generation. But here in Mesopotamia, sophistication appears before its building blocks. The Sumerians mapped the heavens before they should understand astronomy. They work with geometric ratios before mathematics supposedly exists. They describe chemical processes in tablets thousands of years before medieval alchemy. And then there are the objects themselves. Small, mysterious, technically advanced, sitting in museum drawers like splinters from a timeline that doesn't fit. One artifact in particular haunts the edges of regular archaeology, found in layers associated with Mesopotamian civilization, now held behind glass or in storage, depending on which museum worker you ask. Its composition is unsettling. Highly pure copper, careful construction, signs of repeated use. When researchers rebuilt similar objects, they discovered something that shouldn't be possible. They work not as ritual objects, not as symbolic tools. They function as devices generating electrical potential or focusing light with optical precision that requires an understanding of physics the ancient world supposedly lacked. The scholarly response has been mostly silence, a few papers with cautious language, theories about accidental discovery or ritual purpose misunderstood by modern eyes. But no satisfying explanation for why these objects exist, or how Bronze Age craftsmen achieved precision that can barely be copied with hand tools today. Meanwhile, the Sumerian tablets themselves offer a strange kind of testimony. Among their inventories and king lists and hymns, scribes describe instruments that sound almost technological: vessels of shining copper that store the fire, stones that make seeing clear, liquid mixtures that harden like metal. For decades, scholars read these as poetic metaphor. But what if they were catalog descriptions? And beneath it all, another pattern. The Sumerians didn't call their knowledge invented. They called it restored. Their word for the codes and formulas of civilization, the me, were described as divine gifts brought back after a great catastrophe, after a flood that destroyed the world that came before. At night, when conservation labs go dark and artifacts rust in their controlled environments, you can almost feel the weight of that word: restoration, not innovation, not discovery, the recovery of something that already existed once. The same way a fingerprint in dried clay holds the shape of a hand that pressed it 5,000 years ago, these artifacts hold the shape of knowledge we are not supposed to find in the Bronze Age. Each one, a small, stubborn refusal to fit the timeline we've built. Perhaps that's why they remain so quietly catalogued, why most documentaries skip over them, why textbooks prefer the clean story of gradual progress. Because if one small copper cylinder or crystal lens can function as technology, real, deliberate engineered technology, then the entire foundation of our historical timeline begins to crack. The sand keeps more secrets than we've yet had the courage to dig up. If these artifacts shouldn't exist in the Sumerian world, then where did the knowledge to create them actually come from? The answer might lie in a single object waiting in a museum vault where temperature and humidity are carefully controlled. But to understand why that object matters, we need to return to the moment it was pulled from the ground, to the heat and silence of southern Iraq, where the desert still holds the color of forgotten time. Picture the excavation sites of the early 1900s. British teams under Leonard Woolley at Ur, German archaeologists at Uruk, French expeditions near Nineveh and Nimrud. These weren't treasure hunters looking for gold. They were scholars expecting to find humanity's first stumbling steps, crude stone tools, basic clay bowls, the earliest attempts at record-keeping scratched into wet earth. The desert gave them something else entirely. When Woolley's team cut through the mounded tells near Ur, they found layered cities stacked like pages in a book. Each layer revealed not progression, but consistency. The deeper they dug, the more sophisticated the finds became. Temples with foundations aligned to true north. Drainage systems engineered with consistent slopes. Tablets filled with commercial contracts, medical recipes, and star charts that track celestial movements across decades. The heat shimmered over excavation trenches as workers hauled up basket after basket of artifacts. Clay seals depicting intricate mythological scenes. Cylinder seals rolled across wet clay to prove authenticity, a concept that requires both abstract thinking and institutional trust. Musical instruments with precisely measured strings. Weights and measures standardized across hundreds of miles. Sumer didn't crawl towards civilization. It stepped into it wearing full regalia. But scattered among these expected finds, the tablets, the pottery, the temple foundations were objects that didn't quite fit the narrative. Small oddities that excavators would wrap carefully in cloth and mark with question marks in field journals. At Nimrud, British archaeologist Austin Henry Layard uncovered a piece of polished rock crystal ground into a curved shape with optical properties. At various Mesopotamian sites, teams found ceramic vessels containing copper cylinders, sometimes with iron rods positioned in the center, the interiors stained with substances that suggested chemical reactions. Stone vessels made of diorite, one of the hardest stones available, showed drill holes with perfectly round circles, as if cut by machinery rather than hand tools. Most of these items were catalogued with deliberately vague language: ritual object, decorative tool, vessel of unknown purpose. They were packed into crates, shipped to museums in London, Berlin, Baghdad, and quietly placed in storage drawers or minor display cases, because they created problems that had no easy answers. The rock crystal lens, for example, when modern researchers examined it under magnification, they found it had been ground with such precision that it could focus light effectively, requiring an understanding of focal lengths and curvature that shouldn't exist in the ancient world. The ceramic upper cylinders, when rebuilt and filled with acidic solutions, generated measurable voltage. The diorite vessels showed machining marks that copper or bronze tools shouldn't be able to produce. These weren't crude experiments. They were refined products. And they sat in museum collections, labeled but not explained, for decades. One artifact in particular draws attention from those willing to look closely. It resides now in climatic-controlled storage. Some say in Baghdad's National Museum, others claim specimens exist in British and German collections. The exact origin varies depending on which researcher you consult, but the essential characteristics remain consistent. It's a clay jar, roughly cylindrical, about 5 inches tall, on glaze, unremarkable in appearance. The kind of vessel that could easily be overlooked in a collection of thousands. But inside this particular jar sits a copper cylinder fitted precisely to the interior dimensions. And suspended within the copper cylinder, held in place by an asphalt seal at the top, is an iron rod that shows signs of corrosion, not from age alone, but from chemical exposure. When conservators first cleaned such objects, they noticed the staining patterns of acidic residue, consistent with substances like vinegar or citrus juice. The copper showed oxidation in patterns suggesting repeated filling and emptying. The iron rod's corrosion was concentrated where it would have been submerged in liquid. In the 1930s, German archaeologist Wilhelm Koenig, working in Iraq, examined several of these objects and proposed something that made his colleagues deeply uncomfortable. He suggested they might be galvanic cells, primitive batteries. His idea was mostly ignored. Too strange, too out of place. Batteries require not just materials, but understanding, knowledge of electrochemistry, of how different metals and acidic solutions create electrical potential. The ancient world wasn't supposed to possess that knowledge. But then researchers built replicas. They filled them with vinegar, inserted the copper and iron components exactly as found in the original artifacts, and measured the results. Voltage small but measurable, enough to power electroplating operations, or perhaps to create the sensation of divine presence in temple rituals. Enough to prove the design wasn't accidental. The rock crystal lenses present a similar problem. To grind crystal into a precise optical curve requires not just patience, but geometric understanding. You must know how light bends, how curvature affects focus. An inward lens, when tested, showed optical properties consistent with deliberate engineering, not the random polish of decorative work. And this is where the Sumerian timeline becomes truly unsettling. These aren't isolated oddities. They're part of a pattern. Across Mesopotamian sites, archaeologists kept finding objects that demanded more technical knowledge than the Bronze Age was supposed to have. Precision drilling in hard stone, complex alloys, chemical processes described in tablets, astronomical observations requiring multi-generational record-keeping. Sumer already challenges our understanding by appearing too advanced too quickly. But these artifacts, these functional devices, push the question deeper. They suggest not just sophisticated culture, but sophisticated science, applied physics, practical chemistry, engineering that serves a purpose. The copper and clay vessels weren't made once by accident. Multiple examples exist with consistent construction methods. The crystal lenses appear in different sites, ground to similar specifications. The precision drilling shows up across hundreds of stone vessels, all exhibiting the same machining characteristics. Someone knew what they were doing, and they knew it long before our textbooks say such knowledge existed. The artifacts sit in their climatic-controlled environments, small and quiet. Most museum visitors walk past them without a second glance. They look primitive next to the grand sculptures and golden treasures. But that's precisely what makes them dangerous to the accepted narrative. Because if these objects truly function as technology, if they represent applied scientific knowledge in the 3rd millennium BC, then every assumption about the linear development of human civilization needs to be reconsidered. The question isn't whether ancient people were clever. We know they were. The question is, where did this particular kind of cleverness come from? How did Bronze Age craftsmen learn to manipulate chemical reactions for electrical generation? Who taught them optical principles? What tradition preserved this knowledge when it couldn't have been derived from simple trial and error? The desert wind still moves across the ruins of Ur-Qadr, carrying dust that might contain flakes of copper, fragments of crystal, molecules of ancient chemistry. And in the vaults, behind locked doors and archival labels, the artifacts wait. But what exactly is this artifact? And why does it break the rules of the ancient world so completely that many scholars would rather not talk about it at all? The most studied example was discovered in 1936 at Kujit Rabu, just outside Baghdad, in a layer dated to approximately 250 BC, the Parthian period. But the design itself, and similar objects found in earlier Mesopotamian contexts, point to knowledge that predates the Parthians by centuries, possibly inherited from Sumerian and Babylonian scientific traditions. The object measures roughly 13 centimeters tall and 8 centimeters in diameter. At first glance, it's unremarkable. A terracotta jar, pale yellow-brown, with a narrow neck. The kind of vessel that could have held wine, oil, or grain. Thousands of similar jars sit in museum storage worldwide. But this one is different. Inside the clay vessel sits a copper cylinder, fitted so precisely to the interior that there's barely any gap between metal and ceramic. The copper sheet has been rolled and soldered along a seam, evidence of controlled metalworking. The bottom of the copper cylinder is sealed with a copper disc, also soldered in place. At the top, an asphalt plug secures everything. And through that plug runs an iron rod, positioned centrally, suspended so it doesn't touch the copper walls. When Wilhelm Koenig first examined it in the Baghdad Museum, he noticed the iron rod was heavily corroded, but not uniformly. The corrosion pattern suggested exposure to an acidic substance, something more aggressive than simple groundwater. The copper cylinder showed green oxidation stains, particularly along the interior surfaces, consistent with repeated contact with an electrolyte solution. The archaeological context matters here. The artifact was found alongside other domestic items: clay pots, agricultural tools, oil lamps, clay tablets documenting grain transactions. Nothing particularly ceremonial. Nothing that screamed temple ritual or royal treasure. It was in a house, perhaps a workshop, stored with everyday objects. Yet its construction speaks to anything but everyday purpose. Look closer at the engineering. The copper cylinder's wall thickness is remarkably consistent, roughly 1 millimeter throughout. The iron rod is positioned with careful alignment, held at the center by the asphalt seal to prevent contact with the copper. This isn't an accidental arrangement. This is deliberate design, the kind that requires both planning and purpose. When you hold a replica in your hands, you can feel the weight of intention. The components fit together with a logic that suggests function over symbolism. The sealed bottom prevents leakage. The narrow opening at the top allows filling and emptying. The central rod, suspended in space, waiting for something to happen around it. Koenig's interpretation was straightforward, but radical. This was a galvanic cell, a battery. The archaeological establishment responded with polite skepticism. Ritual objects, they suggested. Perhaps a scroll container. Maybe a vessel for storing sacred texts. The iron rod could be a support structure. The copper lining might prevent moisture damage. The asphalt seal was simply good craftsmanship. But then researchers at the British Science Museum built exact replicas in 1978. They filled the vessels with various acidic solutions: grape juice, vinegar, copper sulfate. They inserted a copper cylinder and iron rod in the precise configuration of the original. And they measured voltage between 0.8 and nearly 2 volts, depending on the electrolyte used. Enough electrical potential to power electroplating operations, coating silver objects with gold, for instance. Or perhaps enough to create tingling sensations for temple initiates touching sacred objects, making the divine presence feel tangibly electric. The experiments prove the design works. Whether it was intended to work that way remains the uncomfortable question scholars prefer to avoid. Meanwhile, the rock crystal lenses present their own engineering mystery. The Nimrod lens, discovered by Layard in the 1850s, is an oval piece of polished rock crystal, roughly 4 centimeters long. One surface is flat, the other ground into a precise curve. When examined under magnification, it shows no random scratches or irregular polish. The curvature is deliberate, consistent, mathematically calculated. Modern optical testing confirms it has a focal length of about 11 centimeters, and can magnify up to 3 times. It could have been used to examine fine detail for engraving cylinder seals, perhaps, or for astronomical observations, or even for starting fires by focusing sunlight. But creating such an object requires understanding optics. You must know that curved surfaces bend light, that different curvatures produce different focal lengths, that rock crystal's transparency makes it superior to polished metal. This isn't knowledge you stumble upon while making decorative beads. The mainstream explanation is that these lenses were merely decorative jewelry inlays for furniture, symbolic objects representing the eye of God. But that explanation fails when confronted with the precision of the grind. Decorative objects don't require accurate focal lengths. These lenses do what lenses are supposed to do: focus light. Here's the problem that keeps surfacing whether we're examining the copper and clay vessels or the crystal lenses. We encounter the same unsettling reality. These objects require prerequisite knowledge. To build a functioning galvanic cell, you need to understand that different metals in acidic solutions create electrical potential. You need to know that the metals must not touch, that the electrolyte must make contact with both, that the configuration matters. This isn't trial and error. This is applied electrochemistry. To grind an optical lens, you need geometric principles. You must understand how light refracts through curved surfaces, how focal length relates to curvature, how crystal clarity affects image quality. You need both theoretical knowledge and practical technique. And yet our timeline places these objects in periods when such knowledge supposedly didn't exist. The Parthians inherited Mesopotamian scientific traditions, yes. But those traditions trace back through Babylon to Sumer, cultures we've been taught were just discovering agriculture and basic metalworking. The artifacts sit in their display cases, small enough to cup in your palm, but they carry implications too large to comfortably catalog. They suggest not primitive experimentation, but mature technology. Not accidental discovery, but intentional engineering. Not the beginning of science, but perhaps the remnants of it. Is this artifact a lone accident of history, or is it just one piece of a much larger pattern hiding in the ruins of Mesopotamia? The answer emerges when you stop looking at individual curiosities and start seeing the collection as a whole. Walk through the storage rooms of the British Museum, the Baghdad Museum, the Louvre. Past the famous sculptures and golden treasures, tucked into drawers labeled miscellaneous or displayed without fanfare, sits an entire category of objects that share one troubling characteristic: they're too sophisticated for when they were made. The drill hulls appear first precise circular penetrations in stone that should have resisted ancient tools. Diorite vessels from Sumerian sites show perfectly cylindrical bores, some penetrating several inches deep. Diorite ranks 7 on the Mohs hardness scale, harder than any copper or bronze tool the Sumerians supposedly possessed. Yet the drill marks are smooth, round, exhibiting the kind of consistent pressure and rotation speed that suggests something more controlled than a hand-crank bow drill. Petrie discovered similar oddities in Egypt during his surveys of the 1880s. He measured core samples extracted from granite and diorite, finding spiral grooves that indicated the drill descended into the stone at a rate far exceeding what copper tools should achieve. He calculated that some drills must have cut through granite with a ton of pressure behind them, advancing at rates that made him question the entire accepted tool inventory of the ancient world. In Mesopotamia, the same impossible precision appears. Stone bowls carved from materials that should have taken months to shape show symmetrical curves and uniform wall thickness. The interiors are smooth, the rims perfectly level. When examined under magnification, the polishing marks run in directions that suggest rotational tools, something spinning consistently, not the irregular hand strokes of manual abrasion. But the drilling is just one thread in a larger tapestry. Metal analysis reveals another. Bronze Age Mesopotamian sites have yielded metal objects containing alloy compositions that shouldn't exist. Small tools and decorative items show traces of nickel, antimony, and other elements not native to the region. Someone was either importing exotic metals from tremendous distances, or had access to metallurgical knowledge that allowed precise combination of trace elements. At Teep-Gor, a site in northern Iraq with occupation layers predating Sumer, archaeologists uncovered copper objects dated to 5000 BC, pushing metalworking back into periods traditionally associated with stone tools alone. The sophistication appears earlier than expected, as if the technology arrived fully developed, rather than evolving slowly from crude experiments. Meanwhile, those crystal lenses aren't unique. Multiple examples exist across Mesopotamian sites, all ground with similar precision. Some researchers argue they're decorative inlays, but the explanation falters when you examine the optical quality. These objects focus light. They magnify. They perform the function lenses are designed to perform, which suggests their makers understood that function. The pattern extends beyond tools and technical objects. Administrative artifacts reveal mathematical sophistication that mirrors the physical precision. Clay tablets document BASC-60 calculations, geometric formulas for field measurement, astronomical observations tracking planetary movements across years. The Sumerians divided the circle into 360 degrees, the hour into 60 minutes, conventions we still use today. This level of abstract mathematical thinking doesn't emerge from societies struggling with basic survival. And then you look beyond Mesopotamia, and the pattern expands further. In Egypt, the precision stonework of the Old Kingdom presents similar mysteries. The granite sarcophagus in the king's chamber of the Great Pyramid shows tool marks that Petrie described as astonishing. The interior corners are sharp, the surfaces flat to within 1/1000th of an inch. The blocks fit together so tightly that a razor blade barely slides between them. Whether this represents lost techniques or simply extreme patience remains debated, but it demonstrates capabilities our reconstructions of ancient technology struggle to explain. In Anatolia, Göbekli Tepe pushes the timeline of sophisticated construction even further back, to roughly 9500 BC. Massive shaped pillars, some weighing 20 tons, arranged in circles with clear astronomical alignments. Intricate carvings of animals and abstract symbols cover the stone. This wasn't built by nomadic hunter-gatherers scratching out survival. This required organization, planning, specialized labor, and geometric understanding. The Indus Valley civilization, contemporary with Sumer, shows similar unexpected sophistication. Cities laid out on precise grid patterns, standardized weights and measures across hundreds of miles, advanced drainage systems, and urban planning that wouldn't be matched in Europe until Roman times. And like Sumer, the Indus Valley appears suddenly in the archaeological record, already mature. The thread connecting these cultures isn't diffusion or contact, at least not provably so. It's the shared characteristic of arriving on the historical stage already developed, already possessing knowledge that should have taken centuries to accumulate. Back in those museum storage rooms, the miscellaneous artifacts weighed in their climatic control drawers. Each one catalogued cautiously: vessel of unknown purpose, ritual implement, decorative object. The labels are intentionally vague because specific interpretation invites uncomfortable questions. If you call a copper and clay cylinder a battery, you must explain where Bronze Age people learned electrochemistry. If you call a ground crystal an optical lens, you must explain who taught them about focal lengths. If you acknowledge that drill holes and diorite require advanced tool technology, you must revise the entire timeline of human technical development. So instead, the objects receive neutral labels and quiet placement among thousands of other artifacts. They don't make it into textbooks. They rarely appear in documentaries. They occupy the margins of archaeology, acknowledged but not explained, present but not integrated into the standard narrative. Yet together they form a pattern too consistent to dismiss. From Mesopotamia to Egypt, from Anatolia to the Indus, evidence suggests cultures possess technical knowledge beyond what our historical models predict. Not just clever craftsmanship or patient skill, but applied scientific understanding of materials, mathematics, and physical principles. The copper and clay artifact isn't an anomaly. It's an example, one piece of a technological tradition we've only partially excavated, partially understood, and largely ignored, because it doesn't fit the story we've been telling ourselves about the slow march of human progress. If the ground is full of technology that doesn't fit the timeline, do the ancient texts themselves ever admit that their knowledge came from somewhere older, and maybe from someone else? The answer lies pressed into clay, waiting in cuneiform script that has survived 5 millennia. The Sumerians and their successors, the Akkadians, Babylonians, and Assyrians, were obsessive record keepers. They documented everything: grain receipts, legal disputes, astronomical observations, medical prescriptions, and inventories of temple possessions. These weren't poetic compositions or mythological flights. They were administrative records, technical manuals, and catalogs of real objects used in daily life. And hidden in that bureaucratic language are descriptions that sound disturbingly like the artifacts gathering dust in museum storage. In temple inventory lists from Uruk and Ur, scribes catalogued ritual objects with precise terminology. Among the expected items: clay lamps, ceremonial daggers, incense burners, appear phrases that translate awkwardly into modern language: vessels of shining copper, that hold the fire of heaven. At first glance, this reads as metaphor, perhaps a poetic way to describe oil lamps or braziers used in religious ceremonies. But the description becomes more specific. These vessels are distinguished from ordinary lamps. They're described as having inner rods of iron and being filled with sharp water. Sharp water, a phrase that appears in multiple contexts to describe acidic liquids, possibly vinegar or fermented fruit juices. The vessels don't burn oil. They're filled with liquid, and somehow they produce an effect associated with divine presence. When you place this description beside the copper and clay artifact, the one with an iron rod suspended in a copper cylinder, designed to hold liquid, the parallel becomes harder to dismiss as coincidence. Other tablets mention stones that make the distant near, or stones of clarity that bring sight to darkness. These appear in lists of tools used by artisans, particularly seal cutters who carved intricate designs into tiny cylinder seals. The descriptions emphasize clarity, precision, and the ability to see fine details that the naked eye might miss. Rock crystal lenses. Objects that magnify. Tools for close work requiring exact detail. The language is careful, technical, specific. These aren't vague mythological references, but inventory descriptions distinguishing one type of tool from another. The scribes knew these objects existed because they counted them, cataloged them, and noted when they were moved between temples or workshops. Medical tablets offer another window into technical knowledge. Sumerian physicians documented recipes for compounds using precise measurements and multi-step processes. Mix the copper salts with the juice of sour grapes until the liquid turns green. Apply to the skin with a bronze knife, not iron. This isn't folk remedy guesswork. It's chemistry. The instruction to avoid iron tools when working with certain copper compounds suggests understanding of how metals react differently with acids. Other texts describe mixtures that harden like metal but are not metal, possibly referring to early cements or bitumen-based compounds. Instructions specify heating temperatures, cooling times, and proper ratios of ingredients. The precision implies tested knowledge, repeated processes, and understood principles. But perhaps most revealing is the Sumerian concept of the me, a word with no direct English equivalent. The me were divine codes, cosmic principles, blueprints for civilization itself. They included everything from kingship and priesthood to metallurgy, mathematics, and agricultural technique. The me weren't invented by humans, in Sumerian understanding. They were given by the gods, restored after catastrophe, brought down from heaven to rebuild what had been lost. The language is consistent across hundreds of texts. Knowledge came from elsewhere. Civilization wasn't created from scratch. It was remembered, recovered, restored. The Genesis, one of the oldest Sumerian texts, describes the beginning of cities, agriculture, and human culture. But it speaks of these things appearing after a great destruction, after floods wiped away what came before. The gods decide to save humanity and the seeds of civilization by warning the king's Sutter to build a boat and preserve not just living creatures, but also knowledge, the me themselves. This is framing that suggests continuity, not innovation. The Sumerians saw themselves as inheritors, not originators. When you return to the physical artifacts with this textual context, they transform from anomalies into fragments of a remembered system. The copper and clay vessel isn't an accidental discovery. It's the physical manifestation of those vessels of shining copper, catalogued in temple inventories. The crystal lenses aren't decorative accidents. They're the stones of clarity mentioned in artisan tool lists. The texts describe objects that match what archaeologists actually found. The problem is that both the objects and the descriptions require technological understanding our timeline doesn't accommodate. To deliberately construct a galvanic cell, you need electrochemical knowledge. To catalog it as a tool that holds the fire of heaven, you need to have observed its effects, perhaps, the tingling sensation of mild electric current, or the ability to electroplate metals, or some other application we haven't yet identified. To grind optical lenses requires understanding light refraction. To describe them as tools that make distant things near suggests practical use, not symbolic meaning. The tablets also reference a time before temples, before cities, when the world was different. They speak of antediluvian kings who ruled for impossible spans, not as metaphor, but as record. They describe knowledge systems that existed before the flood came up from the earth. And here the artifact, in its museum vault, begins to look less like an invention, and more like a survivor. A piece of technical knowledge that somehow made it through the catastrophe, preserved in the hands of scribes and craftsmen who maintained the tradition even when they might not have fully understood its origins. The copper cylinder, the iron rod, the clay vessel, these aren't Parthian innovations. They're echoes of something older, built according to instructions passed down through generations, catalogued in inventories that trace back to Sumerian temple archives, where the me were carefully guarded and transmitted. The texts admit what the artifact suggests: this knowledge came from somewhere else, some earlier time, some lost world that the Sumerians spent their entire civilization trying to remember and restore. If their knowledge was restored after some great catastrophe, what exactly happened to the world that came before Sumer? The answer appeared first not in tablets, but in mud, a thick, sterile layer of silt that Leonard Woolley's team uncovered at Ur in 1929. They had been digging through occupation layers, cutting down through centuries of human habitation, pottery shards, clay tablets, building foundations, the normal stratification of an ancient city. Then suddenly the artifact stopped. Clean clay. No pottery, no ash, no building debris. Just uniform river silt, 8 feet thick in some places, stretching across the entire excavation site. Woolley kept digging. Below that sterile layer, human occupation resumed different pottery styles, earlier architectural techniques, evidence of a thriving settlement that had been buried, covered completely by flood deposits, then rebuilt on top centuries later. His team measured the extent of the flood layer across multiple dig sites in error. It wasn't localized. It covered the entire ancient city footprint, a massive inundation that had buried the earlier settlement under meters of river-deposited clay. Woolley calculated that such a flood would have required water levels far exceeding normal seasonal flooding. This wasn't the Euphrates overflowing its banks during spring melt. This was catastrophic inundation. Similar flood deposits appeared at other Mesopotamian sites. Excavations at Uruk, Kish, Shuruppak, and Nineveh revealed comparable sterile layers, thick deposits of water-laid sediment, separating older occupation from newer construction. The dates varied slightly by location, suggesting perhaps multiple flooding events between 3000 and 2900 BC, or one massive event that affected different areas at different times. Geologically, the evidence pointed to something real. Not the global deluge of biblical proportions, but certainly regional devastation on a scale that would have wiped out entire populations, destroyed cities, and broken the continuity of whatever civilization existed before. And that's when the ancient texts started making uncomfortable sense. The Sumerian king list describes the world before the flood with strange precision. It names cities Eridu, Batubir, Larak, Sippar, Shuruppak. It lists kings who ruled for impossibly long periods, tens of thousands of years. Then comes the line that appears repeatedly across Mesopotamian literature: the flood swept over. After the flood, kingship descends again, but the reign lengths shrink dramatically, from spans of 30,000 years to reigns of decades and centuries, as if something had changed fundamentally about the world, or about how time was measured or remembered. The Epic of Gilgamesh, in its Akkadian version, tells the story through Utnapishtim, a man warned by the god E to build a boat and save himself, his family, and the seeds of life from a coming deluge. The instructions are specific: seal the vessel with bitumen, load it with animals and craftsmen, bring the seed of all living things. When the flood comes, it's described with terrifying clarity. For 6 days and 6 nights, the winds blew, torrent and tempest and flood overwhelmed the world. When the waters recede, Utnapishtim's boat rests on a mountain, and he releases birds to test if dry land has returned. The Sumerian version, the story of Sutra, tells the same tale with earlier language. The biblical account of Noah mirrors the structure so precisely that scholars have long recognized these as variations of the same cultural memory. But here's what makes the flood narratives particularly striking: they don't just describe water and destruction. They describe the preservation of knowledge. Utnapishtim brings craftsmen aboard, people with skills, technical knowledge, the ability to rebuild. The Me, those divine codes of civilization, are specifically said to be saved and then restored after the waters recede. This is memory framed as continuity. The world before the flood possessed something worth saving: not just biological life, but cultural and technical inheritance. And when you look at the archaeological timeline, the discontinuity becomes visible. Before Sumer's sudden appearance around 3200 BC, there existed earlier settlements: Ubaid culture, Halaf culture, showing gradual development of pottery, agriculture, and basic social organization. Then comes the flood layer. Then comes Sumer, arriving not as a continuation of Ubaid culture, but as something qualitatively different, more sophisticated, more organized, possessing knowledge that seems to exceed what the previous cultures demonstrated. Meanwhile, even earlier sites hint at capabilities that make Sumer's sophistication less anomalous, and more like part of a longer pattern. Göbekli Tepe in southeastern Turkey predates Sumer by more than 6,000 years. Constructed around 9500 BC, it consists of massive shaped limestone pillars arranged in circular enclosures. Some pillars weigh up to 20 tons. They were quarried, transported, shaped, and erected by people we've been taught were nomadic hunter-gatherers just beginning to experiment with agriculture. The craftsmanship is extraordinary. Intricate carvings of animals, lions, foxes, snakes, scorpions cover the pillars. Abstract symbols appear in organized patterns. The circular enclosures align with specific celestial points, suggesting astronomical awareness. This wasn't crude megalithic stacking. This was precision engineering requiring organization, planning, mathematical understanding, and likely some form of social hierarchy to coordinate the labor. Then, around 8000 BC, Göbekli Tepe was deliberately buried. The enclosures were filled with rubble and abandoned. Why remains unknown, but the pattern suggests intentional closure rather than destruction by catastrophe. After Göbekli Tepe, the archaeological record shows what appears to be regression: simpler structures, less monumental architecture. Then, thousands of years later, Sumer rises with its own sophisticated knowledge systems. The timeline doesn't flow smoothly. It moves in waves: sophistication, decline, resurgence, as if human civilization has experienced multiple cycles of rise and disruption, with each new flowering rebuilding from fragments of what came before. Position the copper and clay artifact within this context. If a technological tradition existed before the great floods of the 3rd millennium BC, a tradition sophisticated enough to understand electrochemistry, optics, precision metalwork, then the catastrophic inundation would have destroyed most physical evidence. Cities drowned. Libraries of clay tablets dissolved in floodwater. Tools and instruments buried under meters of silt. But knowledge can survive in other forms: in the memories of survivors, in oral traditions passed from master craftsmen to apprentices, in sacred texts preserved by priestly classes, who saw themselves as guardians of ancient wisdom, in the me, those divine blueprints for civilization that the Sumerians claimed were restored, not invented. Perhaps what we call Sumerian innovation was actually Sumerian remembrance. The tablets they wrote, the temples they built, the astronomical charts they maintained, these might be reconstructions based on fragments preserved through the catastrophe. The copper and clay vessels, the crystal lenses, the precision drilling techniques, these might be surviving technologies from the world before the flood, maintained by specialized groups who understood their function, even if the broader culture had forgotten the full theoretical framework. Woolly's flood layer sits in the stratigraphy like a bookmark, marking where one chapter ended and another began. Above it, Sumer blooms with knowledge that seems too complete, too systematic to be purely novel. Below it, evidence of earlier occupation, settlements that possessed their own sophistication, now buried and fragmentary. And further back, sites like Göbekli Tepe demonstrate that human capability for complex engineering, astronomical observation, and organized construction extends far deeper into prehistory than our textbooks typically acknowledge. The world before Sumer wasn't empty. It was populated by cultures whose achievements we were only beginning to recognize, cultures that rose and fell, and left behind just enough evidence to suggest the timeline of human civilization is far more complex and far more interrupted than the smooth linear progression we prefer to imagine. As Sumer was rebuilding atop the ruins of a drowned world, how did they keep its memory alive? And could that memory be encoded in their language and science just as much as in their artifacts? The answer lies in the oldest written words we can still read, and in the mathematical system we still use to measure time and space. Sumerian is a ghost language. It belongs to no known linguistic family. Not Semitic like Akkadian or Hebrew. Not Indo-European like Greek or Sanskrit. Not related to any language spoken in the surrounding regions or anywhere else in the world. It stands alone in the history of human speech and isolate, appearing fully formed in the earliest written records around 3200 BC, with no clear ancestors, no primitive precursors, no evolutionary trail leading back to simpler forms. When archaeologists first deciphered cuneiform in the 19th century, they expected to find the linguistic equivalent of baby steps, simple word lists, crude grammar, the fumbling attempts of a culture just learning to encode speech into symbols. Instead, the earliest Sumerian tablets demonstrate complex grammar, sophisticated vocabulary, and abstract concepts that require linguistic maturity. The verb system alone is remarkably intricate, with tenses, aspects, and moods that allow precise expression of time, causation, and possibility. The vocabulary includes specialized technical terms for architectural elements, astronomical phenomena, mathematical operations, and administrative procedures. This isn't a language in development. It's a language already developed, being used by scribes who clearly inherited it, rather than invented it. Where did it come from? The absence of linguistic relatives suggests either extreme age so old that any related languages vanished without trace, or isolation from other language groups for so long that connections became unrecognizable. Some linguists have proposed links to Dravidian languages of India or obscure language families of the Caucasus, but these remain speculative at best. What we know for certain is that Sumerian carried information across centuries with remarkable precision. The writing system itself, cuneiform, evolved from pictographic symbols to abstract wedge-shaped characters that could represent both sounds and concepts. This dual functionality allowed scribes to encode complex ideas efficiently, preserving not just words, but the technical knowledge those words described. Meanwhile, the mathematical system embedded in Sumerian culture displays sophistication that shouldn't exist at civilization suppose beginning BASC 60 mathematics. The sexagesimal system appears in the earliest Sumerian records, already mature and systematic. They divided the circle into 360 degrees. They counted time in units of 60 seconds to a minute, 60 minutes to an hour. They use BASC 60 fractions to perform calculations that our modern BASC 10 system handles awkwardly. Why base 60? The standard explanation suggests it's because 60 has many divisors. It can be evenly divided by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes fractional calculations easier. On a third of 60 is 20, on a fourth is 15, on a fifth is 12. practical for a civilization dealing with trade, land measurement, and resource distribution. But that explanation assumes someone deliberately chose base 60 for its mathematical convenience. It assumes a level of abstract mathematical thinking understanding divisibility properties, recognizing the utility of multiple factors that shouldn't exist in a culture supposedly inventing mathematics from scratch. The alternative is that base 60 was inherited, passed down from an earlier tradition that had already worked out the system's advantages, and embedded it so deeply in astronomical observation, timekeeping, and geometric calculation, that later cultures simply maintained it without questioning its origins. Sumerian mathematical tablets demonstrate applied geometry calculating the area of irregular fields, determining the volume of grain storage chambers, solving quadratic equations for construction projects. They used the Pythagorean theorem more than 1,000 years before Pythagoras. They calculated square roots and cube roots. They understood ratios, proportions, and geometric progressions. Clay tablets from the Old Babylonian period, around 1800 BC, show scribal students copying mathematical problems and solutions. These aren't primitive exercises. They're advanced calculations preserved in a teaching tradition that traces back through centuries to Sumerian sources. The Babylonians, who succeeded the Sumerians politically, continued studying Sumerian as a scholarly language long after it ceased to be spoken. For them, Sumerian was like Latin in medieval Europe, a dead language kept alive for religious, legal, and scientific purposes. Priestly schools taught young scribes to read and write Sumerian, to copy ancient texts, to preserve the knowledge encoded in that strange, isolated language. Technical manuals were copied and recopied across generations, medical texts, astronomical observations, mathematical procedures, all maintained in Sumerian, even as the spoken languages of Mesopotamia shifted to Akkadian, then Aramaic. The language became a vessel for preservation, carrying technical knowledge across centuries of political upheaval and cultural change. And here the artifact reappears with new significance. Consider the precision required to construct the copper and clay vessel. The copper cylinder's wall thickness remains consistent within fractions of a millimeter. The iron rod is positioned centrally, suspended at exact alignment. The proportions of cylinder diameter to height follow mathematical ratios that maximize the surface area contact between copper and the acidic electrolyte. This isn't accidental configuration. This is applied geometry, the same geometric thinking that appears in Sumerian architectural plans and field measurement tablets. Someone calculated the optimal dimensions, understood the relationship between surface area and electrical potential, and encoded that knowledge into a reproducible design. Similarly, the rock crystal lenses demonstrate understanding of optical principles that require geometric calculation. The focal length of a lens depends on the radius of curvature, a mathematical relationship. To deliberately grind a crystal to produce a specific focal length requires knowing that relationship and being able to measure curvature precisely. The artifacts, in other words, are mathematics made physical. They represent the application of numerical and geometric understanding, the same understanding, preserved in Sumerian tablets to practical problems involving chemistry and optics. When Babylonian scribes copied ancient Sumerian technical texts, they were preserving not just words, but the scientific principles those words encoded. The language became a storage medium for knowledge that might otherwise have vanished. Even if the physical tools were lost, destroyed in floods, buried in ruins, scattered across abandoned cities, the instructions for rebuilding them could survive in clay tablets written in a language kept alive by scholarly tradition. Perhaps this explains Sumer's paradox, appearing suddenly with sophisticated knowledge, because that knowledge wasn't new, it was remembered. The language carried it. The mathematical system encoded it. The priestly schools transmitted it across generations, maintaining technical traditions, even when the broader culture might not have fully understood their origins. The copper and clay vessels, the crystal lenses, the precision-drilled stone, these become not anomalies, but confirmations. Physical survivals of a scientific tradition mostly preserved in linguistic and mathematical form. The artifact is the exception, the rare case where the actual device survived alongside the written instructions for its construction. Most of the earlier world's technology would have been lost. But if key principles were encoded in a specialized language maintained by scribal schools, embedded in mathematical systems used for timekeeping and astronomical observation, then those principles could resurface centuries later, applied by craftsmen following ancient formulas they might have understood as sacred knowledge rather than scientific technique. Language becomes more than communication. It becomes a time capsule, carrying sophisticated concepts across the catastrophic breaks that destroyed the physical world. The Sumerians wrote in a linguistic isolate, counted in base 60, calculated with geometric precision, and described technical devices in their temple inventories not because they invented these things, but because they inherited a system designed to preserve them. The artifact sits in its museum vault, a small copper and clay cylinder that bridges the gap between linguistic preservation and physical reality. The tablets describe it. The mathematical system explains its proportions. The language carries the instructions. And the object itself proves the knowledge was real, functional, and deliberately engineered. If their language and mathematics carried echoes of a lost science, what happens when modern researchers finally put the artifact itself under the microscope? Does it confirm the myth of inheritance, or expose it as imagination? The answer came in laboratories far removed from the desert ruins, in the controlled environments of museums and research facilities, where modern analytical tools could examine what ancient hands had made. In 1938, Wilhelm Konig's initial examination of the copper and clay vessels was limited to visual inspection and basic chemical tests. He noted the corrosion patterns, measured the dimensions, and proposed his controversial battery hypothesis. But he lacked the technology to analyze the materials at the molecular level, or to precisely measure the artifact's electrical potential. Modern materials science has no such limitations. Spectroscopic analysis of the copper cylinder reveals metal purity consistent with ancient smelting techniques, roughly 98% copper with trace amounts of arsenic and tin. Nothing anomalous there. The copper came from regional sources, processed using methods well documented in Mesopotamian metallurgy. The iron rod shows similar period-appropriate composition bloomery iron with slag inclusions, typical of ancient reduction furnaces. The ceramic vessel itself is fired clay tempered with organic material, matching pottery techniques from the Parthian period and earlier Mesopotamian traditions. The asphalt seal that holds the iron rod in place is natural bitumen, common throughout the region and used extensively in ancient construction and waterproofing. So far, the materials confirm the artifact belongs to a stated period. Nothing exotic, nothing that requires explanation beyond known ancient technology. But then the analysis turns to the corrosion. The iron rod's oxidation pattern is unusual. Standard atmospheric corrosion produces uniform rust across exposed surfaces. This iron shows concentrated corrosion in specific zones, particularly where it would have been submerged if the vessel were filled with liquid to a certain level. Chemical analysis of the corrosion products reveals traces of acetic acid residue, consistent with vinegar or fermented fruit juice. The copper cylinder's interior surface shows green patina copper acetate formed when copper contacts acidic solutions. The distribution isn't random. It's heaviest near the bottom and along the interior walls, exactly where repeated filling and draining would deposit residue over time. This isn't the gradual decay of an empty vessel buried in soil for 2 millennia. This is the chemical signature of deliberate repeated use involving acidic liquids in contact with copper and iron simultaneously. In 1978, researchers at the British Science Museum conducted the definitive reconstruction experiments. They fabricated exact replicas of the copper and clay vessels using period-appropriate materials and techniques. No modern tools, no industrial purity metals. Just copper sheet, clay, iron rods, and asphalt assembled according to the ancient configuration. They filled the vessels with various liquids: grape juice, vinegar, copper sulfate solution, fermented date wine. Then they measured electrical potential between the copper cylinder and iron rod. The results were unambiguous. With vinegar as the electrolyte, the vessels generated between 0.8 and 1.1 volts. With copper sulfate solution, voltage reached nearly 2 volts. The current was weak, measured in milliamps, but consistent and sustained as long as the electrolyte remained fresh. Later experiments by students at Smith College in 2002 replicated these results and extended them, demonstrating that multiple vessels connected in series could generate enough voltage to electroplate silver objects with gold, a technique known to ancient Mesopotamian metalworkers, but previously unexplained in terms of method. The vessels work not as symbolic objects or ritual implements, but as functional galvanic cells producing measurable electrical current through basic electrochemical reactions. Meanwhile, the rock crystal lenses underwent similar scrutiny. Optical testing of the Nimrod lens confirmed a focal length of approximately 11 centimeters, with 3x magnification potential. The grinding shows no evidence of modern machine tools. The surface exhibits minor irregularities consistent with hand polishing using abrasive powders, but the curvature itself is remarkably precise. When measured with modern interferometry, the lens surface deviates from an ideal spherical curve by less than 0.5 mm across its entire face. That level of consistency requires not just patient grinding, but understanding of the relationship between curvature and focal length, and some method of testing focal properties during the grinding process. You don't accidentally grind a crystal to a specific focal length. You do it deliberately, checking your progress, adjusting based on optical performance. This implies both theoretical knowledge, understanding that curved transparent materials focus light, and practical technique, knowing how to test and refine the curve. Comparative analysis reveals where the artifacts fit expectations and where they exceed them. The metalworking techniques are period appropriate. Ancient Mesopotamian smiths could certainly roll copper sheet, solder seams, and warp bloomery iron. The ceramic firing temperatures and clay composition match contemporary pottery. The asphalt waterproofing is standard practice for the region and year. What exceeds expectations is the precision of assembly and the specificity of design. The copper cylinder fits the ceramic vessel with minimal gap, requiring careful measurement and shaping. The iron rod is positioned centrally, held precisely by the asphalt seal, so it doesn't contact the copper walls. The proportions of the component's cylinder diameter, rod length, vessel height follow ratios that maximize surface area contact with the electrolyte. This configuration isn't random. Every element serves a function necessary for electrochemical operation. Remove any component, the copper cylinder, the suspended iron rod, the acidic liquid, and the electrical effect disappears. The design is optimized for its purpose. But here's where the anomaly becomes most striking. If you examine the precision drilling found in associated Mesopotamian stone vessels under high magnification, you find characteristics that challenge conventional tool reconstructions. The drill holes are perfectly cylindrical. No wobble, no variation in diameter from top to bottom. The walls are smooth, showing parallel striations that suggest consistent rotational speed and steady downward pressure. Core samples extracted from hard stone like diorite show spiral grooves, indicating rapid penetration rates. The drill descended into the stone faster than copper tools, working against such hard material should achieve. Experimental archaeology has attempted to replicate these drill holes using reconstructed ancient tools, copper tube drills with sand abrasive, bow drills, weighted drilling apparatus. The results approximate the ancient work, but don't quite match the precision. Modern replications show more irregularity, more variation in hole diameter, slower penetration rates. Either the ancient craftsmen possessed extraordinary skill and patience, spending months on a single vessel, or they had access to techniques we haven't successfully reconstructed. Some researchers have proposed lost drilling methods involving harder abrasives or more sophisticated drill stabilization. Others quietly acknowledge the discrepancy without offering explanation. The scholarly response to these findings splits along predictable lines. Conservative archaeologists emphasize the conventional aspects. The materials are period appropriate, the basic metalworking is well within ancient capabilities, and coincidental functionality doesn't prove intended purpose. They prefer interpretations that avoid technological implications. Ritual vessels, storage containers, symbolic implements whose resemblance to batteries or lenses is purely accidental. But that position becomes harder to maintain when confronted with the reconstruction experiments. The vessels don't accidentally generate voltage. They do so because their design is optimized for electrochemical reactions. The lenses don't accidentally focus light. They do so because they're ground to appropriate curvature. Other scholars adopt a more cautious middle position, acknowledging that the artifact's function is described, but remaining uncertain about original intent. Perhaps ancient craftsmen discovered these effects through trial and error without understanding the underlying principles. Perhaps the electrical sensation was interpreted as divine presence, the optical magnification is magical enhancement. A smaller group suggests something more radical, that these artifacts represent applied scientific knowledge, understanding of electrochemistry and optics, encoded in practical devices, built according to principles transmitted through the very linguistic and mathematical systems that preserved other aspects of Mesopotamian science. The laboratory evidence doesn't resolve the debate, but it does constrain the possibilities. These objects work as devices. Their construction required precision, planning, and repeatability. The materials show signs of deliberate use in ways consistent with their technological interpretation. Whether that technology was discovered, inherited, or transmitted through teaching traditions preserved from an earlier era, remains the question hovering over every test result and measurement. If the artifact really works as a device and not just a symbol, then who taught the Sumerians or their heirs how to build it in the first place? The conventional answer is straightforward: nobody taught them. Ancient Mesopotamian craftsmen, through centuries of metalwork, pottery production, and chemical experimentation, gradually discovered that certain configurations of materials produced interesting effects. The copper and clay vessels were happy accidents, their electrical properties noticed but not understood, perhaps used for temple rituals or metalworking applications without theoretical knowledge of electrochemistry. This explanation has the advantage of requiring no dramatic revisions to our historical timeline. It preserves the narrative of steady technological progress, allows ancient people credit for empirical discovery, and avoids the complications inherent in proposing lost civilizations or forgotten knowledge systems. Trial and error is powerful. Given enough time and enough craftsmen experimenting with materials, useful discoveries emerge. Perhaps a metalworker noticed that copper vessels stored with iron implements and acidic foods produce strange tingling sensations when touched. Perhaps a jeweler grinding rock crystal for decorative inlays accidentally discovered that certain shapes magnified detail, making fine carving work easier. The problem with this explanation is specificity. The copper and clay vessels aren't crude experiments. They're optimized designs, repeated across multiple examples with consistent construction methods. The crystal lenses aren't random grinds that happen to focus light. They're precisely shaped to functional focal lengths. The precision drilling isn't occasional success amid many failures. It's systematic technique applied to hundreds of vessels. Discovery through trial and error leaves evidence failed attempts, gradual refinement, diversity of approaches as different craftsmen tried different solutions. The archaeological record should show primitive versions alongside sophisticated ones, experimental designs alongside proven configurations. Instead, we find the sophisticated versions appearing with little developmental context, as if the final form arrived without the messy process of innovation typically visible in the archaeological record. The alternative explanation is more controversial, but accounts for that specificity. These weren't discoveries, but inheritances. Sumer and its successor cultures preserved fragments of technological knowledge from an earlier tradition, one disrupted by the catastrophic floods that left their mark in the geological record. In this view, the copper and clay vessels and crystal lenses represent the survival of practical devices, whose theoretical foundations were encoded in the linguistic and mathematical systems the Sumerians maintained. The designs were preserved in temple archives, transmitted through scribal schools, and maintained by specialized craftsmen who understood the construction process, even if the broader scientific framework had been lost. This explains why the artifacts appear fully formed, and why their construction follows specific reproducible patterns. They're not experiments. They're reconstructions based on preserved instructions. Meanwhile, the structure of Mesopotamian knowledge transmission supports the possibility of long-term preservation across cultural disruptions. Technical knowledge in ancient Mesopotamia was in public. It concentrated in scribal schools attached to temples and palaces. Young scribes spent years learning cuneiform, copying ancient texts, memorizing technical procedures and mathematical formulas. The curriculum preserved knowledge across generations through deliberate transmission, not through rediscovery, but through teaching. Priestly elites guarded specialized knowledge as sacred property: metalwork secrets, astronomical observations, medicinal recipes, architectural ratios. These weren't general knowledge, but professional mysteries maintained by close guilds. A master craftsman would teach apprentices family techniques passed down through generations, often framing technical procedures in religious language to emphasize their sacred importance. This kind of transmission system can preserve information across catastrophic breaks. If a flood destroys cities but a few priests escape with sacred tablets and technical knowledge, they can re-establish those traditions in new locations. The knowledge survives in human memory, in copied texts, in demonstrated techniques, even if the original context is lost. The flood layers in the archaeological record create exactly the kind of break where such preservation becomes necessary: cities buried under meters of silt, populations displaced or destroyed, material culture disrupted, but knowledge holders surviving and rebuilding, carrying with them the texts and techniques worth preserving. It's entirely possible for sophisticated capabilities to survive in specialized enclaves, while the broader material culture appears simpler. We see this pattern throughout history. During Europe's medieval period, monasteries preserved classical knowledge that had vanished from common use. After Rome's collapse, certain craft guilds maintained engineering techniques for centuries, even as overall technological complexity declined. The same principle could apply to post-flood Mesopotamia. If technical knowledge was already concentrated in priestly schools before the catastrophe, those institutions could have preserved and transmitted it afterward, even if physical infrastructure and population were devastated. And this pattern isn't unique to Mesopotamia. Cultures worldwide preserve myths of culturbringers, divine or semi-divine figures who taught humanity essential skills. The Egyptians spoke of Thoth, who brought writing, mathematics, and astronomy. The Greeks told of Prometheus bringing fire and technical arts. Mesoamerican traditions describe Quetzalcoatl teaching agriculture, architecture, and calendar systems. The Vedic texts of India mention the 7 sages who preserved knowledge. Through a great deluge. The conventional interpretation treats these as mythological archetypes, universal human patterns of attributing cultural achievements to heroic founders. But there's another possibility: these myths preserve cultural memory of actual knowledge transmission from earlier groups to later ones. Not aliens, not supernatural beings, but human teachers from civilizations or cultural groups that predated the ones who recorded the myths. Teachers whose real identities were lost to time, but whose contribution to knowledge survived as legend. If Göbekli Tepe demonstrates sophisticated engineering 6,000 years before Sumer, and if flood layers mark catastrophic breaks around 2900 BC, then the timeline allows for earlier human cultures, sophisticated enough to develop technologies that later societies inherited as fragments and memories. The myths of culturbringers could be exactly what they claim to be: memories of a time when knowledge came from somewhere else, from people who possessed it before the flood, before the break, before the world changed. The copper and clay artifact becomes, in this context, more than an archaeological puzzle. It becomes a physical metaphor for the entire question of inheritance versus innovation. Small enough to hold in your hand, unremarkable enough to be catalogued quietly and forgotten, yet functional enough to demonstrate that ancient people possessed applied scientific knowledge we didn't expect them to have. It doesn't fit the narrative of slow technological progress from primitive beginnings. It sits stubbornly in the record alongside the crystal lenses and the precision drilling and the BASC-60 mathematics and the flood myths, as one more piece of evidence that the story is more complex than we've been telling ourselves. Whether you interpret it as the product of trial and error discovery or as a survivor from an earlier technological tradition, depends on which anomalies you're willing to take seriously, and which you prefer to explain away. Conservative archaeology chooses the path of minimal disruption to existing models. Alternative archaeology follows the threads of evidence that suggest discontinuity, inheritance, and forgotten sophistication. The laboratory evidence doesn't resolve the debate because the question isn't really about one artifact. It's about what we're willing to consider possible in human history, whether we allow for the complexity of civilizations rising and falling, knowledge preserved and lost, traditions transmitted across catastrophic breaks in ways that leave fragmentary evidence. The artifact sits in its vault, silent but functional, waiting for someone willing to ask the harder questions about where it really came from. If this single artifact can bend the edges of our timeline, what does it say about the story we tell ourselves that human civilization is young, linear, and fully understood? Perhaps it says we've been telling ourselves a simpler story than the evidence supports. A story with clear beginnings and predictable progressions, where humanity climbs steadily from crude stone tools to bronze metallurgy to scientific enlightenment, each step following logically from the last. The copper and clay artifact and all the anomalies surrounding it suggests something messier, history interrupted by catastrophe, preserved in fragments, transmitted through cultural memory that our modern skepticism dismisses too quickly as myth. We may never know with absolute certainty what the ancient craftsmen intended when they assembled copper cylinders and iron rods in clay vessels, or when they ground rock crystal to precise optical curves. But we know enough to recognize that the timeline isn't as straightforward as our textbooks prefer. We know that sophisticated knowledge appears earlier than expected, that techniques we can barely replicate existed in the Bronze Age, that the Sumerians themselves claim to be restoring rather than inventing their civilization. And we know that sometimes, when we're honest about what the evidence shows rather than what it should show, the past becomes stranger and more complex than the neat progression we've constructed to explain it. Night settles over the museums now. The fluorescent lights dim in climatic-controlled storage rooms where thousands of artifacts rest in numbered drawers. In display halls, security lights cast long shadows across cases filled with clay tablets, cylinder seals, stone sculptures of forgotten kings. The day's visitors have gone home, and the ancient objects return to their patient vigil, waiting as they've waited for millennia, holding their secrets in copper and crystal and cuneiform script. Somewhere in that darkness sits the artifact. Perhaps in Baghdad, perhaps in London or Berlin. The copper has dulled to green patina. The clay vessel shows cracks from its time underground. The iron rod, corroded by centuries and by whatever acidic liquid once filled the space between metal and ceramic, rests in its suspended position aligned, deliberate, purposeful, even in stillness. The flight catches the crystal lenses in an adjacent case. They might gleam faintly smooth curves ground by hands that understood how transparent stone bends light, how curvature creates focus, how vision can be enhanced through deliberate shaping of natural materials. These objects don't announce themselves. They don't demand attention the way golden treasures or monumental sculptures do. They sit quietly among thousands of other small things pulled from the earth: pottery shards, broken tools, fragments of daily life in the ancient world. But they carry weight beyond their size. They represent questions we haven't fully answered about who knew what and when, about how knowledge travels through time, about what survives when civilizations fall. Meanwhile, 7,000 miles from those museum vaults, wind moves across the rocky desert. It passes over the ruins of Uruk, where ziggurat foundations still rise from the sand like the bones of a giant. It carries dust across Tel al-Mikhair, where Wooley's excavation trenches cut down through the flood layer that marks the world's division into before and after. The same wind that culled Sumerian scribes bent over clay tablets in 3000 BC, now whispers through empty foundations and buried streets. The same sun that witnessed the construction of the first cities, now sets over their remnants, walls softened by erosion, bricks returning to the earth they came from, temples slowly dissolving back into the landscape. Beneath that sand lie older layers, still cities built before the flood, settlements whose names we don't know, foundations that predate Sumer itself. And somewhere in that stratification, buried under meters of silt and millennia of accumulated dust, might rest other artifacts, other examples of knowledge that doesn't fit our comfortable timeline. The world that produced the copper and clay vessels also produced the king list, with its impossible reign lengths, the flood myths that mirror geological reality, the BASC-60 mathematics we still use, the astronomical tables tracking Venus, the medical texts describing chemical processes, the linguistic system that appears fully formed with no clear ancestor. Sumer wasn't the first civilization. It was the first civilization to remember, to systematically record and preserve what came before, to frame its own achievements as restoration rather than innovation, to maintain scribal schools that copied ancient texts, long after the language that wrote them had ceased to be spoken. The artifact becomes a symbol for that act of remembrance, a physical fragment of technical knowledge, transmitted across the catastrophic break that divided the world into antediluvian and post-flood eras. Whether its makers fully understood the electrochemical principles they were applying, or whether they followed instructions preserved from an earlier scientific tradition, it represents the survival of sophisticated knowledge through disruption. Knowledge can live in many forms in mathematical systems embedded so deeply in culture that no one questions their origin, in language structures that carry technical concepts across centuries, in myths that preserve historical memory under symbolic language, in priestly schools that guard sacred formulas and ritualized procedures, in artifacts that demonstrate principles their makers may have understood practically but not theoretically. Every civilization that falls leaves breadcrumbs, objects that don't quite fit, that suggest capabilities beyond what we expected, that whisper of knowledge systems more sophisticated than survival should have allowed. Future archaeologists examining our own ruins, if such a future comes, will find their own anomalies, technologies whose full function they might not understand, devices that seem too advanced for their context, evidence of capabilities that don't match the simple narratives they construct about our time. We are not the first complex society. We are not the first to possess scientific understanding or technical capability. We are simply the latest in what may be a much longer sequence of rises and falls, blooms and catastrophes, knowledge gained and knowledge lost. The artifact suggests we exist within a cycle, rather than at the pinnacle of a straight line, that human capability for sophisticated thought, for engineering, for scientific observation, stretches deeper into prehistory than we've been willing to acknowledge. That the neat division between primitive ancient peoples and advanced modern societies is more fiction than fact, a story we tell ourselves to feel special, to claim progress, to pretend we've escaped the patterns that caught previous civilizations. But objects like the copper and clay vessel, the crystal lenses, the precision-drilled stone, they refuse the simple story. They sit in their cases and drawers, small and quiet, not fitting the narrative, not disappearing despite scholarly discomfort. They wait, the way truth waits, patient, persistent, willing to be ignored, but unable to be erased. Perhaps that's the real gift of artifacts that don't fit. They force humility. They remind us that history is deeper than our records, that human capability is older than our timelines, that the story of civilization is more complex than the linear progression from crude to sophisticated that we've constructed to organize the past. The museum lights stay dim through the night. The artifacts rest in their controlled environments, temperature and humidity carefully monitored to prevent further decay. Outside, the world turns through its hours, and the same questions hover over the ancient objects that have hovered over them since archaeologists first pulled them from the earth. Where did this come from? Who made it? What did they know that we thought they couldn't know? And what does it mean that these objects exist at all? If one small Sumerian artifact can whisper that our history is older, stranger, and more advanced than we think, what else is still sleeping in the ground, waiting for someone willing to listen?